Hello and welcome back to Mr. Latham's AQA revision session. So today we're looking at P2.3, Work Done, Energy and Momentum Part 2. And in this revision session I'm going to be talking almost exclusively about momentum. So to start off with, we need to understand a little bit about what momentum is. Now momentum is a product of mass and velocity. So it's calculated by multiplying the mass of an object by its velocity. Now, as with so many of the other formulae that you have to remember, should I say, for P2, this is actually one that you don't need to revise because of the fact it is given on your formula sheet. However, you will need to remember the units for these, for momentum, mass and velocity, and they are given as follows. So mass is measured in kilograms, velocity is measured in meters per second, and momentum is measured in kilogram meters per second. Now it's very important that when you're writing the units for momentum that you put the forward slash in the correct place. So it is kilogram meters per second. So the slash goes between the M and the S and not between the K, G and the M. Very important that you remember where to put the forward slash. Okay, now I have represented this also as a formula triangle, and I'll just really quickly show you how I generated that. So having a look at the formula that we are given, they give us momentum equals mass multiplied by velocity. I have a look at these two variables and I can see that these two are multiplied. Therefore they occupy the two bottom slots on the formula triangle. As such, momentum, which is represented as a lowercase p, occupies the top slot. Okay then, so let's have a look at a question. So a car with a mass of 1,200 kilograms is travelling at 8 meters per second. What is the momentum of the vehicle? So what do we need to do? Well, to start off with, we need to have a look and check that our units are correct. So our car has a mass of 1,200 kilograms. I can see that those units are correct. They're in kilograms, which is what they need to be in, and I can also see that the velocity is 8 meters per second and the velocity is meters per second. Therefore I don't need to convert any units first. I can simply multiply these two numbers together. So momentum is mass multiplied by velocity, therefore the momentum of the car is 1,200 multiplied by 8, which gives us 9,600 kilogram meters per second. Once again, very important to remember the units. You quite often get a mark just for writing down the units after your answer. So even if you haven't calculated the answer correctly, you will still achieve a mark if you write down the correct units, which in this case is kilogram meters per second. Okay then, so our next little bit is a very important part of momentum, and it's looking at something called conservation of momentum. And conservation momentum, put simply, just means that the momentum doesn't change during an event. So the momentum before equals the momentum afterwards. And this is very important, especially when we're talking about collisions and when we are talking about explosions. Now in reality this doesn't happen. We're very well, almost impossible to have conservation of momentum because of the fact that momentum is always lost for one reason or another. However, when we are calculating momentum and we're calculating velocities and so on and so forth in collisions and explosions, we have to assume that momentum is conserved. So let's give you an example of a type of question they could ask you which involves conservation of momentum. So we have a boy standing atop a stationary barrel and he falls off, and as he falls off, the barrel rolls away in the opposite direction to him. Explain, using the idea of momentum, why this happens. So we have our boy standing on a barrel, and then all of a sudden, the boy falls off the barrel. Also, as he falls off the barrel rolls backwards in the opposite direction from where he's moving. So why does this happen? Well, it's all to do with conservation of momentum. So a perfect sort of answer for this, so a waggle for this answer would be something such as, before the boy jumps off the barrel, there is zero momentum. And the reason there is zero momentum is because, if you remember back, momentum is mass multiplied by velocity. And since the boy and the barrel are not moving initially, there is no momentum. There is zero momentum, because any mass multiplied by a velocity of zero gives us a momentum of zero. So initially, his momentum and the barrel's momentum is zero. However, as he falls off the barrel, he has momentum. He will now have momentum in one direction, in this case, to the left. Now, because of conservation of momentum, if he has momentum going forwards, then the barrel must have the same momentum but in the opposite direction. So the barrel moves backwards with the same momentum as the boy but in the opposite direction. And this is, as I said before, because of conservation of momentum. The momentum before must equal the momentum afterwards. So the momentum before was zero because nothing was moving. If he moves in one direction with a momentum, then the barrel must have equal but opposite momentum in the opposite direction. Therefore, the two momentums would cancel out, and therefore the net momentum would also be zero. Okay then, so let's now look at collisions. So momentum with regards to collisions. And as you can see at the top, I've put the momentum formula there, just because we'll be needing to use that in a sec. So in this example, we have two blocks. We have a yellow block here, or an orangey block, orangey yellow, and this block is a stationary block with a mass of 150 kilograms. And as you can see, a red block, which has a mass of 500 kilograms, collides with it. Now this block, before it collides, has a velocity of 2.5 meters per second. So, start off with, what is the momentum of the boxes before the collision? Well, firstly, our yellowy orange box is not moving. As it says in the question, it is stationary. Since it is stationary, we have its mass multiplied by zero. Therefore, its momentum is zero. On the other hand, the red block is moving, and it has a mass of 500 kilograms, and it is moving at 2.5 meters per second. Therefore, the momentum of the red block is 500 multiplied by 2.5. So its mass multiplied by its velocity, which gives us 1,250 kilogram meters per second. Therefore, the momentum before the collision is 1,250, since the yellow block isn't moving and the red block is moving with a momentum of 1,250 kilogram meters per second. So, what is the momentum after the collision? Well, quite simply, the momentum is the same. The momentum after the collision is also 1,250, and this is because of conservation of momentum. As we saw in the last example, the momentum before the collision was 1,250, so the momentum after the collision must also be 1,250. So our final question is, what is the velocity of the combined boxes after the collision? So as you can see, with the collision, the red block hits the yellow block, and then they both move together away. So, what is the velocity of the combined boxes? Well, to work out velocity, we'll go to our formula triangle at the top. We put our finger or our cursor over the velocity, and you can see it is momentum divided by mass. So we have our momentum, which we got from our last question, the momentum of the blocks afterwards, and we divide that by the mass of the combined boxes. And it is important to remember these are combined boxes, so actually we can treat this yellow and red box as actually a single box now, and it is a single box with a combined mass of, in this case, 650 kilograms, because we have 500 for the red and 150 kilograms for the yellow. So combine those two together, 500 plus 150 gives us 650. So our momentum is 1,250, our mass or combined mass is 650, divide these two, and therefore our velocity is 1.923 dot dot dot. There's a few other numbers on the calculator. So to round that to 3 significant figures, which is the general rule of thumb for science, gives us an answer of 1.92 meters per second. Once again, important to remember the units. The question is asking us for the velocity of the box, of the boxes, therefore our units will be meters per second. Okay then, so our next bit's talking about explosions. So once again, we need to remember the fact that we have conservation of momentum. The momentum before the event equals the momentum after the event. So we have a cannon, and it is about to shoot a cannonball. And we can see that the cannon has a mass of 3,000 kilograms, and it is shooting a 16 kilogram cannonball at a velocity of 510 meters per second. What is the recoil velocity of the cannon? So let's have a look. So cannonball is shot, and we now have motion. So we have the cannonballs moving to the right, and the cannon is recoiling to the left. Now, whenever you're doing questions involving explosions, what I would strongly recommend is, if they give you a diagram, use it. Label it, draw arrows on it, draw numbers, write numbers on it, and so on and so forth. And if they don't give you a diagram, I strongly recommend that you doodle one. It doesn't have to be a detailed diagram, but just something so that you can visualize what's happening, and generally speaking, it makes it much easier to be able to calculate and not get mixed up with the numbers. So that's exactly what I'm going to do with my two examples. So to start off with, you can see that we have the cannon has a mass of 3,000 kilograms, and our cannonball has a mass of 16 kilograms. Also, the cannonball had a velocity of 510 meters per second. So what do we need to calculate? Well, we need to calculate the velocity of this cannon rolling backwards. But we can't work this out yet, because the only thing we know about the cannon is its mass. We don't know its momentum, therefore we are not able to calculate its recoil velocity. However, we do know the velocity and the mass of the cannonball, therefore we are going to start off by calculating the momentum of the cannonball. Now, to work out momentum is just mass multiplied by velocity, so therefore we multiply these two numbers together. Now, you can see the units are already correct, so I don't need to convert anything first. So I simply multiply the two together, and it gives me an answer of 8,160 kilogram meters per second. Now let's label that on my diagram, just so I know where the numbers come from. Now, this is the important part. Because of conservation of momentum, we know that the cannon, before the cannonball was shot, that the cannon and the cannonball weren't moving. Therefore, their momentum before the cannon was shot was 0, because nothing was moving. However, once the cannon shot the cannonball, we can see that the cannonball quite clearly has a momentum. Moreover, it has a momentum of 8,160 kilogram meters per second. Therefore, if the cannonball has a momentum of 8,160, then the cannon must also have a momentum of 8,160. Otherwise, there wouldn't be conservation of momentum. So because there was no momentum before the cannon was shot, if afterwards the cannonball has this momentum, then the cannon must have an equal but opposite momentum. So therefore the momentum of the cannon is also 8,160 kilogram meters per second. And now we can calculate the velocity of the cannon. We now have the momentum and the mass, so we can now go ahead and calculate its recoil velocity. So we go to the formula triangle and we put our cursor over the V, so you can see it is momentum divided by mass. Its momentum 8,160 and its mass is 3,000. Put that into a calculator and the answer is 2.72 meters per second. And there's our answer. Okay, so let's look at another example then. So a tank fires a 50 kilogram projectile at a velocity of 820 meters per second. The tank recoils with a velocity of 0.68 meters per second. What is the mass of the tank? Okay, so the first thing I would do if I was given this question is I would go ahead and doodle a diagram, since they haven't given me one. So if I just go on to another slide, I've just rewritten the question at the top, and I've just done a little silly doodle here. It's nothing very complicated, and it doesn't need to be. The whole point of this is to be able to calculate the answer. You do not want to waste 5 minutes of the exam drawing a detailed diagram of a tank and a projectile. Therefore, I've just represented this as a couple of rectangles to represent the tank, and this object to represent the projectile. So as with the last question, I'm going to proceed to label the elements I've been given. So the projectile has a mass of 50 kilograms, and it is shot at a velocity of 820 meters per second. So I've also labelled that there. Now what about the tank? Now the tank, we need to calculate the mass. So we need to calculate the mass, and we know its recoil velocity. So the first thing we're going to need to do is to calculate the momentum of the projectile, and we can then use that to calculate the mass of the tank. So the projectile, the momentum of the projectile is mass multiplied by velocity, taken from our momentum formula triangle, which is 820, our velocity, multiplied by our mass of 50, which gives us a value of 41,000 kilogram meters per second. So now we can look at our tank, because now we have from the question the recoil velocity of the tank, which was 0.68, and we now have the momentum of the tank, which was 41,000 kilogram meters per second, and this number we have got just because it is going to be the same as the momentum of the projectile. As it was with the last question, the momentum before equals momentum afterwards. Before the tank shot the projectile, there wasn't any momentum. Therefore, if the projectile is shot with a momentum of 41,000, then the tank must also have a momentum in the opposite direction of the same value. So now all I need to do is then rearrange the equation, or use my formula triangle to calculate the mass of the tank. So I'm going to put my cursor over M, and you can see to calculate mass, it is momentum divided by velocity. So our momentum is 41,000 and our velocity is 0.68. Put that into a calculator, and the answer we get is 60,294 kilograms, which sounds reasonable for a tank. The 60 metric tons, that's probably about right for a tank that's shooting a projectile of that sort of mass. So there we have it. There is our final answer for the mass of the tank. Okay then, so our next bit is talking about impact forces. Now impact forces is, as the name implies, it is the force of an impact as one object hits another object. And it can be affected by three factors. Firstly, the mass of the object. Secondly, the acceleration of the object, or the change in velocity of the object. And finally, the duration of the impact. Now, how we calculate the impact force is using the equation below. So impact force is the end momentum minus the start momentum divided by the time or the duration of the impact. Now we can actually simplify this to simply say that the impact force is the change in momentum. So end take away start is the change in momentum over the duration or the time. Now unfortunately, this is again one of those equations that they do not give you, a little bit like the speed, distance, time equation. So you will need to remember this. Alternatively, if it's not something that you wish to remember, you can instead use two equations that they do give you. However, from personal experience, students find it more difficult to use these two equations to calculate the impact force. If you did want to use these equations, you would simply start off by calculating the acceleration of the object by looking at the end velocity and the start velocity. So end velocity take away start velocity, divided by time. So that will give us our acceleration, but then you then need to substitute that into here. So then you have your value from the top equation, put it into there, so then you have the acceleration, and you then multiply this by the mass of the object to give you the impact force. Now, it is doable, but as I said, it does make the process a little bit more tricky. There's more places where you could perhaps make a mistake and then not get the correct answer. So instead, you can just calculate it using this, in my opinion, more simple equation of change in momentum divided by time. Okay then, so let's have a look at an example. So again, we have a cannon shooting a cannonball, and this cannonball has a mass of 20 kilograms, and it hits a ship whilst it's travelling at 65 meters per second. Now the cannonball is stopped by the hull of the ship, so it collides with the ship, and it stops the cannonball in 0.01 second. What is the impact force? So I've just written down there our formula. Impact force is change in momentum divided by time. So first thing we need to do before we can calculate the impact force is we need to work out the momentum before and the momentum afterwards. Okay then, so our momentum before, well, the cannonball has a mass of 20 kilograms and it's moving at a velocity of 65 meters per second before it collided with the ship. Therefore its momentum is 20 multiplied by 65, which gives us a momentum of 1,300 kilogram meters per second. Relatively straightforward, just looking at our momentum equation. Momentum equals mass multiplied by velocity that we used on the previous slide. What about the momentum afterwards then? Well, that's quite simple really, because if you read the question, it does say that the cannonball is stopped. Keyword there, stopped by the hull of the ship. Therefore, at the end, the cannonball's not moving. Therefore, its momentum is 0, because any mass multiplied by 0 is going to give us a momentum of 0. Therefore, our change in momentum is our momentum at the end, which is 0 kilogram meters per second. Take away or subtract our momentum before. So our change in momentum there is minus 1,300 kilogram meters per second. And now we have our momentum, or should I say our change momentum. We now just simply need to divide this by the time taken to stop the cannonball, which in this case is 0.01 seconds. So we put that into our calculator. Minus 1,300 divided by 0.01 gives us an impact force of minus 130,000 newtons. Very important to make sure you include the units. Yes, we are talking about a force, an impact force, and as we know from previous videos, that forces are measured in newtons. Okay then, so let's look at a slightly trickier one then. So this is a question talking about a batsman hitting a baseball. So we have a baseball which has a mass of 0.25 kilograms being hit by a batsman when it is moving at 30 meters per second, and the batsman hits it in the opposite direction with a velocity of 15 meters per second, and the ball is in contact with the bat for 0.002 seconds. Calculate the impact force of the bat on the ball. Now this is a little bit tricky, and the reason why it's a little bit trickier is because of the fact that the ball actually doesn't come to a stop. So we need to be careful when we're calculating this to make sure we don't slip up. But we calculate it in the same way. So start off with, what was the momentum before the baseball was hit? So we have a mass of 0.25 and we have a velocity of 30 meters per second. Therefore the momentum before is 7.5 kilogram meters per second. So what is the momentum after the ball was hit? So after the ball was hit, we have the momentum being, well, the mass is the same, so we still have the baseball having a mass of 0.25 kilograms, but this time it says that the ball is moving in the opposite direction with a velocity of 15 meters per second. Now because it's moving in an opposite direction than it was before, we represent this as a minus 15 meters per second. So our calculation is 0.25 multiplied by minus 15, which gives us a momentum of minus 3.75. And this doesn't mean it's necessarily negative momentum, it just means it's momentum in the opposite direction. Okay, so then when we calculate our change in momentum, it is our momentum afterwards, which is minus 3.75, subtract our momentum before the impact, which is 7.5, and minus 3.75 minus 7.5 gives us minus 11.25 kilogram meters per second. It's very important that you realize that you have minus 3 minus 7, so we have a negative taking away another negative, which is making us have a much greater negative number of 11.25. So then what we need to do, just to finish the equation off, is then divide this by the impact time. And the impact time in this question is 0.002 seconds. So we then just divide our change in momentum by the time taken, and we can see that our impact force is minus 5,625 newtons. Okay then, so our final stop then is just a little mention about car safety. Now this isn't something I'm going to speak about very much, it's just something that I want to mention. If you did want to go away and do a little bit more research on it, then go ahead, but I wouldn't spend too long researching into this. Alright, just make yourself aware of the basics. And they do all really work on the same kind of principles, which is all to do with momentum. So firstly, we have airbags. So I'm sure you've all heard of airbags, and most people have airbags in their cars these days. And what does an airbag do? Well, during the collision, as there is an impact, the airbag inflates, and then it cushions the blow, so to speak. Now, if you were to write that in an exam, that the airbag would cushion the blow, then unfortunately you're not going to receive any marks for that, because it's not really very scientific. So we need to be able to explain this with regards to momentum. And how we would explain it is the fact that an airbag increases the duration, the time of the impact. And that's what happens when your head or any part of your body hits an airbag. It increases the duration of the impact because it deflates as your head hits it. So there's a much greater impact time. And secondly, it also decreases the rate of change of momentum. Okay, I'll say that again. It decreases the rate of change of momentum. In other words, it causes the momentum to drop much more gradually. And both of these causes there to be a lower impact force, therefore reducing the injury on the individual. Okay, secondly, we have crumple zones. Now, crumple zones are found at the front of the car and at the rear of the car, and these are generally found in the bumper regions, and their function's pretty straightforward really. They are there to crumple during a collision, and what they do is, as you collide with another vehicle or with another object, they crumple, and by crumpling they increase the duration of the impact. So the impact takes place over a longer period of time, therefore it reduces the impact force. And finally, we then have seatbelts. And seatbelts, they work by increasing again the duration of the impact. And secondly, they decrease the rate of change of the momentum, just like the airbags do. And finally, they also spread the force over a larger area. Okay, so instead of it just being your head hitting the steering wheel or the dashboard or whatever, it is spreading that same force over the whole of your chest, therefore decreasing the force exerted. Okay, so all of these, the whole point of these safety features that we have in cars are all put in place to reduce injuries and fatalities of the people that are in the vehicles. Okay, and that's it. So thank you for listening.